Hello everyone, welcome to Neso Academy. In the previous lecture, we implemented our first VHDL code in Vivado, where we learned how to create source files, how to write the VHDL code in Vivado code editor, how to generate the RTL schematic, and how to analyze the simulation waveforms. And today, we are going to understand how to implement all 7 logic gates in Vivado. Now, logic gates are the building blocks of the digital systems. Now, why we are calling these building blocks logic gates as logic gates? Because they act like a real physical gate. Just like a physical gate allows or blocks people, a logic gate allows or blocks the flow of data based on the mathematical logic. Meaning, a logic gate makes logical decision to generate the output based on the mathematical logic of the input combination. For example, an AND gate decides to generate the output if input A and input B both are active. So, what are logic gates? Logic gates allow or block the flow of data based on the mathematical logic. And I hope you understand this. So, in this lecture, we will implement all 7 logic gates using VHDL with the help of data flow modeling. Why data flow modeling? Because logic gates are based on Boolean equations, and we have already studied that data flow modeling is the most suitable choice for the Boolean expression. Now, let's understand all 7 logic gates one by one, starting with the first basic logic gate, the AND gate. Logic gates are categorized into basic logic gates, universal logic gates, and derived logic gates. Now, basic logic gates include AND gate, OR gate, NOT gate. Now, why we are calling them as basic logic gates? Because they are the fundamental building blocks for all digital circuits. We can create any complex circuit by using these basic logic gates combination, where AND gate represents logical multiplication, OR gate represents logical addition, NOT gate represents logical inversion. Now, let's get back to the AND gate. AND gate returns 1 when all inputs are 1. So, in case of AND gate, output will be 1 when all inputs are 1. Let's understand this using the 2 input AND gates truth table. So, this is the truth table of 2 input AND gate. Here we have 2 inputs A and B and one output Y. For 2 inputs, we will have 4 input combinations 0, 0, 0, 1, 1, 0, 1, 1. Now let's see the output for the first input combination. Here output Y is equal to 0 when both inputs A and B are 0, because AND gate returns 1 when all inputs are 1, and here both inputs are 0. Therefore, the output is 0. Now look at the second input combination. Now here A is 0 and B is 1. In this case, output Y is 0, because here we can see input A is 0. Now in the third input combination, when A is 1 and B is 0, output will be 0. Now look at the last and the fourth input combination when both inputs A and B are 1. Now in this case, output is 1, because here we can clearly see output is 1 when all inputs, and here when both inputs are 1. So, I hope you understand this truth table. Now, the reason why we are calling this gate as an AND gate is because it acts like the English word AND. Here, output requires input A and input B both to be 1 in order to generate the output as 1. Therefore, we are calling this gate as the AND gate. And I hope you understand this. Now let's see the symbol for the 2-input AND gate. Now this is the symbol of the 2-input AND gate, which looks like a letter D. Here we have 2 inputs, A and B, and output Y. And I hope you understand what is the AND gate. Now let's see the second basic logic gate, OR gate. OR gate returns 1 when at least one input is 1. So, in an OR gate, the output is 1 when any single input is active or 1. Now, let's understand this using the 2-input OR gates truth table. Here we can see we have 4 input combinations. Now look at the first input combination. When both inputs A and B are equal to 0, that's why the output Y is 0. Because as per the definition of the OR gate, output will be 1 when at least one input is 1. And here in the first input combination, both inputs are 0. Therefore, the output is 0. Now look at the second input combination. A is 0, B is 1. Now here B is 1. Therefore, the output is 1. In the third input combination, A is 1, B is 0. Now here A is 1. Therefore, the output is 1. In the last input combination, both inputs are 1. So, output is 1. And I hope you understand why we are calling this gate as the OR gate, because it acts like the inclusive English word OR, in which output becomes 1 if input A or input B or both of them are 1 or active. So, I hope you understand why we are calling this gate as the OR gate. Now, let's see the symbol for the OR gate. Now, this is the symbol for the 2-input OR gate. On the input side, it has a curved shape or a concave shape, which represents a funnel which takes multiple input combinations and generate a single output. So, we are done with the OR gate. Now, let's understand the third basic logic gate, NOT gate. NOT gate returns the opposite value of the input. So, the output is the NOT of the input. So, 0 becomes 1 and 1 becomes 0. In the truth table, when input is 0, output will be 1, and when input is 1, output will be 0. So, NOT gate returns the opposite value of the input. Now, let's see the symbol of the NOT gate. It includes a triangle pointing to the right with a bubble at the end. Now, what happens if we remove this bubble? We are left with this triangle, and this triangle represents a buffer. Now, what is a buffer? Buffer is a circuit which passes the same signal as it is. So, in buffer, this input A will reflect as it is at the output Y. So, by adding this bubble, we are inverting the input. So, this bubble is performing the inversion operation of the input. So, I hope you understand all three basic logic gates. Now, let's see the universal gates. Universal gates include NAND gate and NOR gate. And why we are calling them as universal gates? Because by using either NAND gates or NOR gates, we can implement any other logic gates or any other digital circuit in the universe. Therefore, we are calling them as universal gates. Now, let's see the NAND gate. Now, here the word NAND means not plus AND. So, NAND gate is the inverse of the AND gate. Therefore, it returns 0 only when all inputs are 1. So, in NAND gate, output will be 0 when all inputs are 1. Let's understand this using the truth table. Here we have 4 input combinations, and for 4 input combinations, the outputs are 1, 1, 1, 0. In the case of the AND gate, the outputs were 0, 0, 0, 1. So, NAND gate is the inverse of the AND gate. In the truth table, we can see NAND gate returns 0 when all inputs are 1. So, I hope you understand why NAND gate is the inverse of the AND gate. Now, let's see the symbol of the NAND gate. NAND gate is the AND gate with inverted output. Here, bubble represents the inversion of the AND gate. So, we are done with the NAND gate. Now, let's see the second universal gate, NOR gate. Now, the keyword NOR means not plus OR. So, NOR gate is the inversion of the OR gate. Therefore, NOR gate returns 1 only when all inputs are 0. When all inputs are 0, then in the case of NOR gate, the output will be 1. Now, let's see the truth table. Here, we have 4 input combinations. Now, look at the first input combination when A is 0 and B is 0. So, here both inputs are 0. That's why the output is 1. And as per the definition of the NOR gate returns 1 when all inputs are 0. And for other input combinations, outputs are 0. So, here outputs are 1, 0, 0, 0. And in the case of the OR gate, the outputs were 0, 1, 1, 1. So, NOR gate is the inverse of the OR gate. Now, let's see the symbol for the NOR gate. So, NOR gate is the OR gate with the inverted output. Now, here the bubble represents the inversion of the OR gate. So, I hope you understand the universal gates. Now, let's see the third category of the logic gates, derived gates. Derived gates include XOR gate and XNOR gate. Now, why we are calling them as derived gates? Because they are derived using the basic logic gates, AND gate, OR gate, NOT gate. Now, let's see the first derived logic gate, XOR gate. XOR gate returns 1 when the inputs are different. So, in XOR gate, output will be 1 when all inputs are different. Now, the word XOR means exclusive OR. Here, output will be 1 if input A is 1 or input B is 1. Here we are excluding the condition. The output will be 1 when all inputs are 1. Therefore, XOR gate is an exclusive OR. Now, to understand this in a better way, let's see the truth table. Here we have 4 input combinations. Now look at the first input combination. When both inputs A and B are equal to 0, which means both inputs A and B are same. Therefore, the output is 0. In the second input combination, when A is 0 and B is 1. So here both inputs are different. Therefore, output is 1. In the third input combination, when A is 1, B is 0. Again, here we have different inputs. Therefore, output is 1. In the last input combination, when A is 1, B is 1. So, both inputs are same. That's why output is 0. So, I hope you understand this truth table. Now, focus on these 2 input combinations for which the output is 1. Now, in these 2 input combinations, there is a single 1, which means odd number of 1. So, whenever there are odd number of 1s in the input combinations, the output will be 1. So, the XOR gate is also called as odd ones detector. And I hope you understand this. Now, let's see the symbol for the XOR gate. Now, the symbol includes the same OR gate along with the curved line. Now, this extra curved line represents the exclusiveness of the XOR gate. So, I hope you understand the XOR gate. Now, let's see the second derived logic gate, which is XNOR gate. Now, XNOR gate is the inverse of the XOR gate, which means XNOR gate returns 1 when the inputs are same. So, output will be 1 when inputs are same. Let's understand this using the truth table. Here in the 4 input combinations, look at the first input combination when A is 0 and B is 0, which means both inputs are same. That's why the output is 1. In the second and in the third input combinations, both input combinations have different inputs. Therefore, the output is 0. In the last input combination, both inputs A and B are equal to 1. Therefore, the output is 1. Now, in the case of the XOR gate, the outputs were 0, 1, 1, 0. But in the case of XNOR gate, the outputs are 1, 0, 0, 1. So, XNOR gate is the opposite of the XOR gate. Now, let's see the symbol of the XNOR gate. Now, the symbol includes the XOR gate along with the bubble. So, XOR gate with inverted output. So, I hope you understand all 7 logic gates. Now, let's implement them using Vivado with the help of data flow modeling using VHDL. So, we are in Vivado and this is the data flow modeling code for the 7 logic gates. Now, if we want, we can change this light theme interface into a dark theme based on your Vivado version. For that, go to Tools and select Settings. Now click on Try the new Vivado IDE. Then click on OK. Now click on this Vivado setting as OK. Now you just need to restart your software. Means close this software and reopen it. Now, after restarting our software, this is our new Vivado IDE. Now, in order to change this light theme into a dark theme, go to Tools, click on Settings. On the left-hand side, in the Tool Settings, click on Text Editor. Then select VHDL. Now, here we can see Themes option. Currently, it is a light theme. Change this light theme into a dark theme. It will take only few seconds. Just wait. Now, this is our dark themed interface. Close this notification. Now, let's get back to the VHDL code. Now, our code starts with IEEE library with standard logic package from the IEEE library. After library declaration, here we have entity. And here I have named this entity as logic_gates. Now, inside the entity, we will declare the input and output ports. Now, as discussed in the presentation, we have understood 2 input AND gate, 2 input OR gate, 2 input NAND gate, 2 input NOR gate, 2 input XOR gate, 2 input XNOR gate and a NOT gate. Therefore, I have declared here 2 inputs A and B as standard logic data type. And to represent the 7 outputs of the 7 logic gates, here I have represented the 7 signals and _G is representing the output of AND gate as standard logic data type. OR _G signal is representing the output of an OR gate as standard logic data type. NOT _G signal is representing the output of the NOT gate as standard logic data type. And similarly, here I have declared the remaining outputs. Now we can close this entity with the keyword END and with the name of the entity logic_gates. After entity declaration, we will have our architecture. Architecture name as data flow because we are writing the Boolean equations of logic_gates is, and after the keyword begin, we can write the Boolean expressions using the logical operators. Here we are using 7 logical operators: AND operator, OR operator, NOT operator, NAND operator, NOR operator, XOR operator, and XNOR operator to represent the Boolean expressions. Now, look at the first Boolean expression, A and B. We are assigning this A and B in the AND underscore G signal. Similarly, A or B and storing the result inside the signal or underscore G. Not A means we are taking a complement of the signal A and storing the result inside the output signal not underscore G. In the same way, we can perform other Boolean expressions for the other logic gates as well. Now, I hope you understand this data flow modeling code for all 7 logic gates using the all 7 logical operators. Now, let's see the schematic diagram generated by Vivado. For that, go to RTL Analysis, click on Open Elaborated Design and select Schematic. So, this is the schematic diagram generated by Vivado. Here we have 2 inputs, A and B, and 7 outputs representing the 7 outputs of the 7 logic gates. Now, let's verify this schematic. Here, output AND underscore G is equal to A and B. Output OR underscore G is equal to A or B. Now, for NAND gate and NOR gate, Vivado does not have any specific symbols. Therefore, Vivado represents them using the complemented form of the AND gate and the complemented form of the OR gate. So, NAND underscore G is equal to the complement of A and B. NOR underscore G is equal to the complement of A or B. Now, the next output NOT underscore G is the complement of input signal A. Similarly, we can see XOR gate output and XNOR gate output. Here, XOR underscore G is equal to A XOR B and XNOR underscore G is equal to A XNOR B. So, I hope you understand this schematic diagram. Now, in data flow modeling, the Boolean expressions are directly converted into the schematic diagram. Now, let's see the simulation waveforms generated by Vivado. For that, go to Simulation, click on Run Simulation and select Run Behavioral Simulation. Now, this is our simulation waveform window. Here we have our 2 inputs, A and B, and 7 outputs. Now, let us verify our VHDL code for all 4 input combinations. For that, let me quickly assign the input values manually. Now, how to do that? Let me show you. Right-click on signal A, select force constant to apply the values manually. Now, select value radix as binary because we want to apply binary numbers 0 and 1. Now, force value 0, then click on OK. Similarly, for signal B, right-click on signal B, select force constant, value radix as binary, and force value as 0. Now, this is our first input combination 0, 0. Similarly, you can assign other 3 input combinations as well. Let me quickly assign them. Now, I have assigned all 4 input combinations and I have simulated each input combination for 100 nanoseconds. Now, let's see the generated waveform. Let me maximize this waveform. And here we have all 4 input combinations 0, 0, 0, 1, 1, 0 and 1, 1. Now, let's verify our code for one input combination. Let's say for 0, 1, when A is equal to 0 and B is equal to 1. Now, what will be 0 and 1? It will be 0. And here we can see and underscore G is equal to 0, which is correct. Now, what will be 0 or 1? It will be 1. And here we can see or underscore G is equal to 1, which is correct. Now, not of A, which is equal to not of 0, which will be 1. And here we can see not underscore G is equal to 1. Now, what will be 0 NAND 1? It will be 1. And here we can see NAND is equal to 1. Now, what about 0 NOR 1? It should be 0. And here we can see NOR is equal to 0. Now, what about 0 XOR 1? Here we have a single 1. And we all know that an XOR gate is the odd ones detector. Therefore, it will be 1. And if XOR is 1, XNOR will be 0. And here we can see XNOR is equal to 0, which means our code is absolutely correct. And I hope you understand the implementation of all 7 logic gates using data flow modeling in Vivado. So, in this lecture, we understood all 7 logic gates and we have also implemented them in Vivado using data flow modeling. With that, we are done with this topic of logic gates using VHDL in Vivado. So, we are done with this lecture. I will see you in the next one. Thank you.